Hello everyone. Today we're going to talk about related rate. So it's a application of our implicit differentiation. So now we're just going to have to be really careful about our variables and how we use our notation. Right. So we're going to just do this by looking at two different word problems. Right. So I'll start by writing it down. So we have water runs into a conical tank at a rate of 9 feet cubed per minute. So conical, just meaning a cone. Sometimes it'll be inverted cone. You'll see that wording. Or in this case, we'll say the tank stands point down. Same thing, inverted point down, and has a height of 10 feet. So our cone's 10 feet, and the base radius of 5 feet. How fast is the water level rising? When the water is 6 feet deep. Right. So we're going to first start by just seeing everything we know. So I'm going to have some cone look something like this. Our cone, we're told, is 10 feet. Okay. So we want to know when our water is 6 feet. So I'm going to call this variable here y, so the height of the water level. And then I'm going to call the radius here x. So the radius of the water, the circle, when the water is 6 feet deep there. So we're going to call that x and y. So what I'm going to want to find is, so this is where we have to be careful with the variables. I want to find dy dt when y equals 6. So I want to know the water level, how fast the water level is rising. So I'm looking at the height with respect to time. So how fast is that water rising? So I want to find dy dt. So let's list all of our variables. So V is going to be volume of the water at time t. So I want to find t. T is time. X is the radius of surface of the water. At t. And then y is depth of water at time t. Okay. And we know that y is 6 feet. We know dv dt is 9 feet cubed per minute. So we know that water's running in at 9 feet per minute. And we also know the volume of a cone. And this is just from geometry. So 1/3 pi x squared y. And we're going to use another equation that we know. So let's say we have this x over y. in comparison to our whole tank. So our mini cone is going to be x over y. We're going to think of it more as a triangle. We're going to use some similar triangle properties. So it's the similar triangle from our water level with a similar triangle to the whole cone. So we know this is 5 over 10. So we're given that the base radius is 5. So the whole tank is 5 over 10. And then that should be equal to the proportion of x over y. And that's, again, by using similar triangles. And now we want to just change this equation around a little bit. This is the same thing as saying x equals y over 2. So I'll let you practice the algebra on that one. 5/10 is 1/2. You can move the equation around and get x equals y over 2. So I'm going to have you try that one as an exercise to get from here to here. Now let's solve the problem. So we're going to use what we did last time with implicit differentiation. So we have volume equals 1/3 pi. And instead of putting our x, I'm going to say y over 2 squared times y. So I'm plugging in that x equals y over 2. And we know this is equal to pi over 12 times y to the third. So all I'm doing here is I'm squaring y, and then I'm multiplying by y, so I get y to the third. 2 times 2, or 2 squared, is 4. 4 times 3 gives me 12 in those denominators, and we have the pi left in that numerator. Okay, so I'm just simplifying this left-hand side. Okay, so now let's find dv dt. So we're using what we got here. So if we have dv dt, this would be pi over 12. We can ignore the constant. 3y squared. But then we also have to multiply by dy dt. We're calling it y prime last class. Same thing, dy dt. Derivative of y with respect to time. And then we can plug in what we know now. We know that dv dt is 9. We can simplify this 3 divided by 12 as well. So I'd have pi over 4 now. So 3 divided by 12 gives me 1 over 4. So I have pi over 4. I can plug in y. Y was 6. So I have 6 squared dy dt. We can keep simplifying now. So I have 9 equals pi over 4 times 6 squared dy dt. So different ways we can move this around. It's going to end up being 1 over pi, however we do it. So let's do 30. So 9 equals pi over 4 times 36 dy dt. So I'm going to end up getting 9 equals 36 divided by 4 would give me 9 pi dy dt. Okay. So I'd have divide both sides by 9 pi. So I'd have 1 over pi equals dy dt. And 1 over pi, if we want an exact, this is about, if we want a number, this is 0.32 feet per minute. You could say 1 over pi feet per minute, that's fine. But we get 0.32 feet per minute. So what this is telling us is the water level is rising at 32 feet per minute. Right. Let's look at one more. So this next example, we're going to have a hot air balloon rising straight up from a field and is tracked by a range finder, 150 meters from liftoff point. At the moment, the range finder elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. We want to know how fast is the balloon rising. At that specific moment. Right. So let's start by drawing a picture. So we have a triangle. We're going to look at some angle theta from the rangefinder. We have our balloon. We'll call this y. So we want to know dy dt. We don't know dy dt. We want to know how fast it's rising at that moment. And we want to know when theta equals pi over 4. So we want to know how fast it's rising when theta is pi over 4. We know this is 150 meters from the question. We also know d theta dt. So the angle is changing by 0.14 radians per minute when theta is pi over 4. This is all when theta is pi over 4. So we're focusing at the specific moment. So theta equals the angle in radians. So it's the angle of the rangefinder makes with the ground. So we say y is the height in meters of balloon. Okay. And now let's try and figure this out. So we have a right triangle, which is nice because we can use our trig functions now. So we can take a look at y divided by 150. Right? So y divided by 150, those are the two things we know. So now we have to think back to trig. So I could have done 150 over y as well, but it's probably a little easier to do y over 150. So y here, that's going to be our opposite. 150 is our adjacent. So we think, what's opposite over adjacent? Opposite over adjacent is tangent. So we have y over 150 is tan theta. You could have done 150 over y and done cotan, but tangent's probably a little bit easier. We know those values a little quicker off the top of our head. And let's just move this around and solve for y. So this is the same thing as saying y equals 150 tan theta. And again, you can do the algebra here, multiply the 150 to both sides, and then that's it. All right, so now we have to take the derivative. Again, it's going to be some implicit differentiation. So we take the derivative of y with respect to time. And then this is equal to 150 times secant squared. So secant squared is the derivative of tangent. So secant squared theta, but we also have to multiply by d theta dt. All right. Now let's plug in here. So I have dy dt is equal. So I did this nicely. We're looking for dy dt. So all we have to do is solve the right-hand side. So we have 150 times secant squared of pi over 4 times 0.14. So dy dt is 150 times root 2 squared. So secant pi over 4 we know is root 2. And then we can just square it from there times 0.14. So root 2 squared is 2. So we have 300 times 0.14. So dy dt is 42. All right. So this tells us the balloon is rising at a rate of 42 meters per minute. All right. So the trickiest part here is finding all of the variables and what functions we have to use to solve these. I'll often use similar types of questions where we use the triangle and some trig functions, and I like the cone example. So I'd recommend writing down the volume of a cone formula. That should be helpful. That's going to be it for today. I hope everyone has a great day, and I'll see you all next class.